So there's a fundamental question about in the field of biomedical optics that can we use light to diagnose a disease? This is a very important fundamental question many people have thought for a long time. So there's a fundamental issues that indicates this is being possible. For example, cells, organelles, ECM proteins are scattering light. And interestingly, what matters is in pathology, you want to see the differences of this scattering property between disease versus normal physiological state. In fact, organelles will be different in disease state. And I put this Greek letter meaning change, okay? Changes in scattering and absorption will be due to changes in the organelle and cellular metabolic products. So that means changes in scattering can be also due to changes in local microenvironment, especially pathological conditions such as necrosis, or inflammation, and angiogenesis. This may also give you a change in absorption. So in essence, optical scattering and also absorption could be an important tool for disease diagnostics. This is a fundamentally very important insight that we can claim and we can utilize light for a disease diagnostics. The reason is especially scattering is the most dominant when this interaction. So scattering is affected by changes in refractive index. The bigger changes, more scattering happens. And also the size of the scatterers, for example, cells. The bigger cells, the more scattering. And also the geometry of the scatter or biological targets, such as a different kind of cells, also matters. For example, because the scattered geometry, such as how many or what kind of shape do they have, will also affect. Also, some specific biomolecules contain very interesting phenomena of polarization alteration we call birefringence. And that could be also utilized for a specific type of detection or imaging system. So another good example for biomedical engineering is utilizing this light scattering in a laser flow cytometer. Cyto means cell, so somehow cell counter, measuring the single cell. So for that, we have to understand, as I say, scattering. So when the light source gets in, the light wave interact with the cell, you can see the cell interaction, there is a forward scattering, also there is side scattering. And in fact, the forward and side scattering contains a little bit different kind of interaction with the cell. So different information can be provided. So we have heard flow cycle, meaning that the cells make in a sheet, sending the cell, individual cell one by one, like this, through a narrow, thin sheet. And then you shine the laser light, and then it interacts with the cells, and then it shows up forward and side scattering. So you just need the two kind of detectors into the forward and side. What the forward actually is more related to the size, and the side scattering is more related to complexity and granularity. Okay, so what are we going to do with this? In fact, we can use this one actually sorting out different components in your whole blood. So whole blood can be analyzed with this. So sorting blood cell types by using laser flow cytometry. And so dual scatter analysis of your whole blood, doing this, you can plot x-axis forward, y-axis side scattering. And this way, and you can see, very interestingly, bigger forward scattering means a bigger cells, and side scattering is more like granularity. So debris and RBC platelets, very small one, they don't scatter much. So these are those. And then there are lymphocytes are simple shape, so they don't side scatter much, but they are bigger than these debris. So they are lymphocytes, T lymphocytes or B lymphocyte. And then remember the origin of macrophage, which is monocytes, are bigger than lymphocytes. And you see the nucleus are more granular, which means more side scattering happens. So you can actually identify those. And granulocytes are not only the size is big, but there are many granules, which allows more side scattering. So even using this, you can actually count the number of different type of cells in your blood. So forward scattering means cell size. Side scattering represents internal complexity or granularity. And this provides differentiating heterogeneous inner side of the blood cell type.